Hi everyone, this lesson is going to be about how we determine the intersection of two planes in three-dimensional space. So I've set up two equations here which represent the Cartesian equations of two planes. The first job is to write down the normal vector for each of these. So I'll say normal vector 1 for plane number 1. Now I hope you remember that the normal vector is the coefficients of the pronumerals. So in this case we would have 1, 2, negative 1 for plane number 1. Normal vector number 2, the coefficients, we have positive 2, negative 3 and positive 1. Notice straight away that normal vector 2 is not a multiple of normal vector 1. Right? So that's important to check. If the normals were the same, or if one was a multiple of the other, then the normals point in the same direction, and that means the planes are parallel. Parallel planes will not intersect. So it's important to note that those normal vectors are independent, not a multiple. So that's good. Now what are we going to do to find the intersection? The intersection line belongs in both planes, and by definition a normal vector is perpendicular to the planes. So the intersection line has to be perpendicular to both normals. The way to find the direction of this, so I'll define a vector D as the cross product between the two normals. The cross product produces a vector perpendicular to both n1 and n2. And now there's various ways to do a cross product of these vectors, but this is the way that I like. So 1, 2, negative 1, 2, negative 3, 1, and we take a determinant of this 3 by 3 matrix. So this first one would be 2 1s are 2, subtract 1 times 3, that's 3, and that's I. Always remember negative for the j component. 1 by 1 is 1 minus negative 2 j component. Then for the negative 3, subtract 4. Okay, let's just simplify. That is negative I, that's plus, so that's minus 3j, and that's minus 7. Okay, that gives me my direction vector D, which could also be expressed as a column vector negative 1, negative 3, negative 7. The line of intersection between the planes will be parallel to that vector, not necessarily exactly equal to that vector. So what we really need to do next is find a point on that line of intersection. Well, looking back at plane 1 and plane number 2, I have here two equations in three unknowns. I will not be able to get a unique solution for these, will I? But I can get a partial solution. What do I mean by that? I mean I can set the value of one of the pronumerals to anything I like and then solve for the other two. Usually we pick something simple like z equals 0. So let's do that. Let's go. Might be an idea. I'll try to get clever here and copy those equations. Let's just try to copy those. Oh, that's a bit of a shaky looking line. Let's see if I can copy that. Come down a bit and then paste them in here. Ah, how nice is that? All right. So I just I don't want to rub all of that out, just that little bit. There we are. So that makes my life a bit easier. So that's equation number 1 again. Remember, plane number 1, and this is plane number 2. So what I'm going to do to solve these guys is I'm going to just arbitrarily choose to let z equal 0. So equation number 1 then would read x plus 2y equals 5. and equation number 2 would read 2x minus 3y equals 2. Now we can solve these two to get a unique solution for x and y, given that z equals 0. So what would I do next? I think I might go 3 times equation 1 plus 2 times equation 2. I notice that the y variables are positive and negative, and if I do that, so 3 times x is 3x, 3 times this is 6y, 2 times 2x is 4x, 2 times that is negative 6y, that's exactly what I wanted, equals, now 3 times 5 is 15, plus 2 times 4, 2 times 2 is 4, so I have 7x equals 19, x equals 19 over 7. Then going back, well, we might as well just go back to equation 1. I have x plus 2y equals 5. 19 over 7 for x plus 2y equals 5. So 2y equals 5. Take 19 over 7. Let's write this all over 7. 7 5s are 35. So 35 take 19, that would be 16. I'm going to divide by the 2, the 7 is still there. That becomes 8 over 7 for y. So a point on my line of intersection, let's say point A, we might as well give it a name. X was 19 over 7. Y is 8 over 7. And remember, we arbitrarily chose that z equals 0. That point exists on the line, on both planes. So it must be on the line of intersection. The direction of my line of intersection is this direction vector d here, 1 minus 3 minus 7. Now that's enough information for me to write the vector equation of the line. So my arbitrary point x, y, z, well, what was point A? It was 19 over 7, 8 over 7 and 0, plus k, and my direction vector was, where did it go? Minus 1, minus 3, minus 7. Minus 1, minus 3, minus 7. That's the vector equation of a straight line. What if I want the Cartesian equation of this same straight line? Well, remember that we read this as x equals 19 over 7 plus k times minus 1. If I read the second row, it'll be y equals 8 over 7 plus k again times minus 3. And the third row would be z equals 0 plus k times minus 7. So let's write those expressions. X equals 19 over 7 minus 1 times k. Y equals 8 over 7 minus 3k, and z equals 0 minus 7k. Rearranging each of these expressions to isolate k, I would have x minus 19 over 7 divided by negative 1. Then I'd have y minus 8 over 7 divided by negative 3, or z subtract 0 over negative 7 equals k. Equating all of these, you can see that each of these are the same, each of these equal k. So the Cartesian form, x minus 19 over 7 over negative 1 y minus 8 over 7 over negative 3, z minus 0 over negative 7. We could tidy that up a little bit if you wanted to, but really not that necessary. So that gives me the intersection of the two planes. Now, just to demonstrate that this isn't all just made up, here is my two equations of the plane in GeoGebra. And there you can see I have an x or y and a z axis, the red, green and blue, and there's the two planes, and they definitely do intersect along a line. Now, if I were to just type the equation of that line, if I can manage to have it on display, there it is, bring GeoGebra back into view a bit. So here I go. For the first one, I will put 19 over 7 subtract x, oh, what did I just do then? 19 over 7 subtract x, good, equals y minus 8 over 7 over negative 3. Can't quite see it there. Yeah. Equals, and what have we got there? Z over negative 7. So let's just bring this along, and what do you know, that blue line there, that blue line that's just appeared, is the equation of that straight line, and that is most definitely the intersection of our two planes. There you have it. That's the end of the process. Thanks for watching.